Hey everyone, thank you for coming in. And today we have Jacob giving our seminar talk. So Jacob's an associate professor at MIT in the Department of Electrical Engineering and Computer Science, as well as the Computer Science and Artificial Intelligence Laboratory. His research spans a lot of things, from computational foundation models of language learning to building intelligent systems, learning with human guidance. He completed his PhD from UC Berkeley. He also has a Master of Philosophy from Cambridge and his bachelor's from Columbia. And he's also received a lot of awards from Sloan Fellowship, NSF Career Awards, as well as like various paper awards at ACL, ICML, NACL. So without further ado, I'll hand it over to Jacob and we'll learn about his interesting insights.
Awesome. Yeah. Thanks again for the introduction. And I guess if it's not too inconvenient with the Zoom format, do feel free to interrupt and ask questions at any point. Happy to keep this interactive. Cool. So I want to start with a really big question, which is the question of what machine learning is about. And the way we present it in intro ML classes, right, it's about building automated systems that can perform some kind of task for us. And typically we specify that task with data, with input-output pairs. Maybe we also have some unlabeled data that tell the model what it's supposed to be doing. As we know, the world as of the last, 5 to 10 years has started to change a little bit. And in particular, we know that now if you use this sort of example-driven technique to train not just any kind of machine learning model, but a language model, you can start to communicate new tasks to that language model, not by providing example input-output pairs, but instead just by providing natural language instructions or natural language descriptions of what it is that you want the model to do. So we can steer things not by collecting data sets, but just by prompting. And so with LMs, we now have this new tool for solving what we sort of motivated as the big ML problem. Even if we don't have examples of our target task, we can specify our desired behavior for the model with language. And if we have a sort of big enough and good enough LM, it'll just follow it. On one hand, this is magical, right? And even with things in the sort of state that they exist in today, I, at least as somebody who, sort of started my NLP research journey in like 2009, often feel like I've woken up in a world where sort of magic lamps and genies exist when you just have these sort of magical systems that you can ask questions. In practice, though, it's also quite annoying to build these systems a lot of the time, right? That there's, to a first approximation, only one way to format a collection of input-output pairs, but there's a million different ways of writing a natural language prompt, and there's a whole literature devoted to showing that even just like very subtle changes in these prompts can cause big and unpredictable changes in how models behave. So if you abstract away from all of this, what machine learning is really about, or at least I think what we want it to be about, is building systems that don't just do what we do, like in these instruction or in these sort of input-output sort of classical ML cases, not just what we say, as in these prompting cases, but ultimately building systems that do what we mean, even if we don't know quite how to articulate what that thing is, either via dataset or in language, right? It's about building methods can go directly sort of from the intentions that live in our heads as human beings into automated systems that operationalize those intentions. Now, I don't think we're quite there yet, but sort of what this talk is going to be about is figuring out how we might get there. And in order to do that, I think it's useful to spend at least a little time thinking about how human beings solve the analogous problem of figuring out sort of what to do in the world. And we do this in a bunch of ways, right? By observing it passively, by experimenting actively, by paying attention to the behavior of the sort of skilled teachers who are around us. And maybe most importantly, and especially if we're interested in building systems with human-like intelligence, we learn from language, which tells us not just what to do, but how to do things and why to do things and sort of what the world is like in a general way. And so something that's going to be a recurring theme in this talk is that learning from language in this sense encompasses a lot more than just being really good at next word prediction, and it entails a lot more than just being able to do instruction following in context, right? That in particular, when we sort of read or hear a sentence, we don't just learn how to generate more sentences like it, but we somehow incorporate the content of that sentence into a sort of complete conceptual model of the world that we're constantly building, and we can do that even just seeing a single fact for a single time. And maybe most importantly, language is not just a passive source of information for learning, but also a tool for gathering information, right? Our teachers use it to figure out what we know now and what we need to learn next. And we, as learners, use language to ask questions and sort of acquire the bits of information that we need when we're ready to consume them. Okay, we've learned a lot in the last decade about how to train systems on huge pre-existing data sets, but I think if we want to really make good on this dream of sort of building systems that can figure out what it is that we're trying to get them to do or what it is that we mean, and then doing that thing, we're going to need to find some way of taking the models that we have right now and equip them with the ability to learn much more efficiently from much smaller amounts of interaction with human users, and then remembering what they got out of those interactions and generalizing in the ways that we expect. Good. So this has been a huge amount of sort of setup, and what this talk is really going to be about is, I think, some first tools that we're going to need to do this. Some of this is work in progress, some of this is sort of speculative, and again, would love to chat with all of you more, and I think there's some time set up for that afterwards. Okay, so the first piece of this talk is going to be about building models that can gather the supervision that they need to perform tasks without requiring users to sort of spoon feed them everything from the get-go. I'm going to be talking here about a couple of papers in collaboration with a bunch of different people. And I guess the first of these was at iClear this year after being on archive for a very long time. Okay, so to start by just like really hammering home one point from the introduction here, even if we want to build a model that implements a simple behavior, right, like recognize pictures containing glasses of beer, people are very, very bad at constructing data sets that uniquely specify these kinds of target behaviors. And so here's a sort of real example from ImageNet classifiers that was actually found by a sort of automated interp tool that I'm not going to be able to talk about today, where it turns out that if you train a model on the ImageNet beer glass, what you actually wind up with is a classifier for images of men holding glasses of beer, not glasses of beer in other contexts, and not women holding glasses of beer. And even in the world of sort of promptable models, it's hard to get systems to do what you want them to do by writing the right prompt. So here's a sort of recent example, and I'm not picking on this paper, it's a cool paper, but buried in an appendix somewhere is a sort of seemingly inconsequential change in a wording of a prompt that just completely makes the difference between this method working and this method not working. So how might we avoid these kinds of issues and start to sort of make good on this goal of learning from figuring out what it is that people actually want and not requiring them to anticipate how the model is going to behave on the basis of one of these noisier forms of specification? It is worth starting out by noting here that this is a question that people have been asking for a long time, and there are good mathematical tools at our disposal here. In particular, there's a long, long line of work on in machine learning on active learning, which I think many people have seen before, that tries to speed this up by sort of starting with a pre-existing set of unlabeled examples and picking examples out of that set one at a time and handing them to a human to label. There's another line of work on what sometimes, in the sort of Bayesian optimization or optimal experiment design literature that actually tries to synthesize from some even larger space of examples the most informative example to label. And you can think of both of these methods as giving us some kind of automated process that we can run that at every step of an interaction with a human annotator is asking, what's the best question that I could ask? And then asking that, subject to the constraint that the only kind of question we're actually allowed to ask our human is, here's an example, here's an X, what's the Y? And of course, the thing that has changed since these methods were originally developed is that now we have automated systems, we have language models that can ask more interesting questions. Now, it's an interesting property, although this is starting to change a little bit. But for the most part, if you're interacting with a language model right now and you ask it sort of underspecified question or a question that contains a bad presupposition or something like that. These models will very often not ask you for clarification and instead just give you some kind of best effort response. And it's worth pointing out that this is a design decision, right? And not sort of an inherent feature of language models as language models as distributions over natural language strings. And in particular, even if you just sort of prompt models to be more aggressive about asking questions, they can actually do it quite well. And so one very simple thing that you can imagine doing is literally just prompting LMs to do information gathering as a sort of substitute for requiring people to write their own instructions. And so the basic sort of paradigm in the experiments we're about to look at right now is we're literally just going to instruct a language model to sort of interview a human user about some target task by asking them a bunch of questions, and then use the sort of transcript of that interview as the prompt for a model that's going to go out and try to perform the task. Now, a note on evaluation before I start showing actual evaluation results. This is not going to be a standard machine learning evaluation setup because what we're really interested in is the extent to which models can sort of personalize themselves, specialize themselves to individual human users' sort of idiosyncratic decisions. And so the way we're going to do all of the evaluations is we're going to say, here's the task, and we'll see some concrete tasks in a minute. The user is going to talk to the language model about the task. And then only after that interview are we going to give the human an unlabeled data set, an unlabeled test set. We're going to ask them to label the test set, and then we're going to see if the language model can predict post hoc the labels that they assign to that test set in some sort of personalized way. This is a very general paradigm. We can imagine applying it to many sort of knowledge-intensive or algorithmic tasks. Here we're going to focus specifically on personalization, on sort of small task families that involve large variation between people in 3 different domains. We're going to look at a content recommendation domain, a sort of email validation like regular expression domain, and a moral decision-making domain. And as we said before, starting by showing off the simplest possible version of this you could imagine instantiating. You prompt a model to ask a user a bunch of questions using something that looks like this, and then you condition on the result of that, on the transcript of that conversation, and you use it to try to label the test set. Okay, so the first thing that you notice is that even if you do this in a sort of zero-shot way, and these are all like GPT, I think even 3.5 or maybe 4.1 era questions, you actually get pretty good questions, and you can get them across a range of domains, right? So here we're in a content recommendation domain. The user or the system says, what kinds of online forums do you use? The user says Reddit. You get a sort of very specific follow-up question that knows something about Reddit and says, what specific subreddits are you interested in? And so on and so forth. And you see similar kinds of things in moral reasoning domains and in more sort of formal like email verification domains. Now, a worry that you might have as a result of this sort of evaluation paradigm that we've set up is that because we're asking people to label a test set after interacting with the language model, is it possible that the language model is actually altering their preferences? And so one way we can get at this is by holding out a set of people, having them not interact with the language model at all, and then for all of those questions on the test set, just look at the sort of proportion of people who answer yes or no to a given question after interacting with the language model and before interacting with or without interacting with the language model. And what we see here is that the proportion of sort of labels doesn't seem to change as a result of question asking. We obviously can't do the counterfactual where people have the interaction, we wipe their brain, and then we ask them to relabel the test set on their own. But it seems like at least at the population level, these kinds of interactions don't change people's preferences in an underlying way. What they do is actually let you improve, in some cases, substantially over all of the other tools that we have right now for specifying target behavior to a model. And so if you ask people to write examples by hand, if you use sort of standard active learning techniques, if you ask the users to sit down and write prompts that specify their behaviors on their own, at least in this content recommendation domain, there's a clear advantage to these sort of language model-based question asking methods. It is less clear that this is the case in some of these other domains, and we'll see sort of slightly improved methods in a minute. In this email domain, there is a significant difference between the quality of the language model questions and the quality of language model predictions based on these interviews and based on user written prompts. It is not actually possible for us to say with certainty that these are significantly better than either of these is significantly better than not doing anything at all. And in the moral reasoning domain, you do substantially better than chance, but people's prompts at specifying that sort of specify their own moral behaviors or moral decisions are also pretty good. Cool. So natural question you can ask at this point is, okay, there's some evidence that having these kinds of interactions with LMs is a better way of getting information out of people's heads into the models. Can we do any better here than literally just prompting these models to ask some questions? And in particular, given that there are these, kind of nice mathematical frameworks for reasoning about uncertainty and quantifying the informativeness of a given question, can we actually use any of these things to do better? And so the way we're going to revisit our sort of old school optimal experiment design techniques is as follows. What prevents us from directly applying these things to the tasks in the previous section is that what we're ultimately interested in getting judgments about free-form natural language text, right? We want the model to be able to read an article and tell the user whether it's going to like the article or not, or whether they're going to like the article or not. And for the most part, the kinds of methods that we have for doing active learning or the kinds of methods that we have for doing optimal experiment design really only know how to work with much, much more structured input spaces with things that look like feature vectors. And so what we're going to do now, in order to be able to apply these kinds of techniques, is to use language models here in a very different kind of role. Rather than asking them to sort of conduct the interviews directly, we're going to use them basically to translate these tasks into a format that then amenable to explicit quantification of sort of what the best questions to ask. And so what we're going to do at a high level is first prompt our language models with problem descriptions, like we want to do content recommendation, and we're going to ask the language models to come up with sort of abstract features that might be relevant for making a decision about whether a user likes an article or not. And so in this content recommendation domain, we're going to think about things like, what's the topic of the article? What's the length of the article? What's the style in which the article is written? And things like that. And we're going to use the language model then to translate back and forth between the sort of raw surface form of the text of articles and these more abstract feature representations that we can sort of use to do question generation in a way that we're going to talk about more precisely in a minute. So to fill this in now with more details, like we said before, what we're going to start with is by saying we're going to have some domain, we're going to have a natural language description of the domain, we're going to ask a language model to come up with a set of features that you could use for predicting whether a person is going to like an article in this content recommendation domain. And using this, we're going to initialize a representation of the user's preference function as just a linear model in the space of features that our language model has defined. And in particular, we're going to maintain a sort of uncertain representation of what it is that the user actually wants as something like a Gaussian distribution, a multivariate Gaussian distribution over the weights that the user assigns to all of those features. And what we're going to do now is at every step of interaction with the user, we're going to look at our representation of their belief, right? This sort of prior distribution, or what's soon going to be a posterior distribution, over what we think the weight they assign to each of these content recommendation features is. And we're going to figure out what is the most informative comparison we could ask for between a pair of features in this domain. And this is something that's actually relatively straightforward to quantify if you know you have a linear model and a sort of normal posterior over the weights on the features, or the weights on that linear model. And so our optimal experiment design technique will say, okay, the most informative question to ask here is to compare the feature vector 1, 0, 0, 0, 0, 1 to the feature vector 0, 1, 0, 0, 1, 0, and so on and so forth. Now, obviously, you cannot go to a human user and say, would you prefer an article with has topic science 1, has topic sports 0, has length 27, and so on, and ask them to like express a preference over these two feature vectors. What you can do is go to a language model and say, here's my feature space, here are some articles with some feature vectors here are some feature vectors that I want to compare. Can you synthesize for me articles that give rise to feature vectors of these kinds? And what pops out are naturalistic looking articles that actually have the features as expressed. And now you can ask the user just for their pairwise preference between these articles. They pick one, and we'll interpret that choice between these natural language articles as a preference in this underlying feature space. And we can use that to then do a sort of standard update to our representation of our belief about the features or the weights that the person assigns to the features in this domain. And so we can repeat this process over and over again. And what will pop out at the end of this is some hopefully much sharper belief about what it is that a person wants to see in an article and what it is that they don't want to see in an article. And then, notably, every article that the person has seen up until this point is fake, right? It was synthesized by a language model as an example of a kind of thing exemplifying some kind of feature vector. At test time, what we want to do is actually rank articles for the real articles for the person. And so we'll just go to those articles. We'll ask our language model now to operate in the other direction, to translate a real article into one of these feature vectors. We'll score that feature vector with this preference vector that we learned for our person, and that'll give us some kind of score. And what we're trying to figure out here is on a sort of article by article basis, are we correctly able to predict whether the person wants to read it or not? So here's a bunch of results. Walking through this actually from the right side to the left side. So starting with this pink bar, I don't know if you can see my mouse, probably not. No, okay. The pink bar on the farthest right, this is actually the same open-ended questions model that performed best in the previous experiment. This is a new set of annotators. This is a slightly different data distribution, but we replicate the previous finding in this new annotator population that you can do substantially better than chance by just prompting people to answer questions about models. Another thing that you can do, rather than letting the language model answer open-ended questions, is to say, let's try these specific pairwise questions that we were generating with this new approach that we tried out right now. And it turns out that models are natively not that good at generating or interpreting these kinds of pairwise questions. And that's the second pink bar on the right. The lightest pink bar in the middle is if we let our sort of fancy question generation procedure that we looked at on the previous slide come up with the questions to answer. And only at test time do we let the language model condition on that whole set of questions and make a recommendation to the user. And it's interesting, and you should maybe be a little surprised by the fact that this is also close to zero. This is basically the language model is failing to do in-context learning with the judgments about these pairwise preferences. Again, these are older models. I think this is all like GPT 3.5, although I can go back and check. And it's possible that current models are better, but it seemed like that's actually sort of hard sort of pairwise preference data is hard to work with for these models in context. We said before that you couldn't possibly ask a user to, give you a judgment about a raw feature vector. Similarly, you could ask a user just like, here's a bunch of features, write down how much you prioritize them one over the other. That doesn't work super well. What does work is either letting the language model ask the questions, whatever pairwise questions it wants, or letting this fancy Bayesian procedure ask whatever questions it wants. And then use those to fit a teeny little linear model in context to the user's preferences and using that to make predictions about what's going to happen next. And so the high level takeaway is that you can actually get better at doing these kinds of question asking tasks, either by letting some sort of automated sort of whatever optimal experiment design procedure or the language model itself choose what questions to ask, but then using the result of those procedures to fit some sort of explicit representation of the user's preferences as a linear model, and actually doing both the question selection and the prediction in linear model space rather than language model space gives you the best results here. Okay. To go very briefly through a couple of sort of fun technical issues that arise when you want to train these kinds of models in other domains. A sort of natural question to ask is, what does this look like once you want to move into more complex domains where you can't necessarily figure out what set of features you want to think about ahead of time? And so we had a cool paper at Coral last year looking at sort of how do you add new features incrementally when you discover that you don't have enough features to explain the user's sort of revealed or expressed preferences. There's some cool work, not from our group, but from folks at Cornell, looking at ways, sort of methods that look like this, but that actually like explicitly parameterize the space of user beliefs as natural language strings. And I think there's a bunch of stuff to do in that direction. And then my student Alexis had a paper at ACL last year on kind of the inverse problem of looking at whether you can infer by asking questions of a human user what it is that they're wrong about when they're trying to do some task, and actually sort of provide more targeted tutoring, again, by reasoning about what's in the user's head by asking them questions, but here where the goal is not to learn something from the user, but instead to teach something to the user. Okay. So sort of summarizing this section, I think the high-level takeaway here is that learning from sort of free-form natural language interactions with human users is sometimes both more accurate, and actually I skipped over that slide, but less cognitively demanding when you ask people sort of interview questions about their cognitive load than the traditional techniques that we've used for getting information out of people's heads and into models. At the same time, current models at least seem to struggle with asking really good questions or interpreting the results of really discriminative questions and benefit from a little bit of scaffolding that helps them figure out things more explicitly. This is not in the talk yet because it's brand new, but I will share also a link to some more question answering work that my student Gabe Grand is doing that is sort of support for this even in like GPT-5 is actually not all that good at asking questions, but you can make it much better with very similar scaffolding to what we were just looking at before. Okay, let's pop up the stack a little. We now have efficient ways of getting natural language information about a task interactively
I had a question
yes.
about the previous topic on just
Oh yeah.
so like two quick clarification questions about the pairwise questions that is asked. Is it just yes or no binary questions, or do you take any kind of other objective questions as well? And two, for the results that you showed, like what's the scale of the number of questions that we're looking at? Like how many in context examples, or how many feet, like, how much information is the LLM gaining before, like, getting those results?
Great. So to the first question, they're not even, it's even more restricted than any yes, no question. It's like they're all of the form, do you prefer thing one to thing two?
Right.
And the paper of Gabe's that I will link to afterwards generalizes that to letting models sort of ask arbitrary binary questions. And you could even generalize it beyond that relatively straightforwardly. But and so I think the surprising thing is that in this very restricted question format, things still work. We in the like experiments from the previous paper over here, I think they're not in the prompt, but we do have what happens if you restrict the model to asking only yes, no questions rather than sort of arbitrary open-ended things. And that's a little worse. So not showing it here. And then to your second question, oh, yeah. So I guess one thing that I haven't actually talked about at all that's maybe an important detail is like what is even on the y-axis in all of these plots. What we're looking at is so the way all of these experiments work is we've sort of capped the duration of the time that the user is either interacting with the model or writing a prompt or labeling examples at 5 minutes. So we're trying to sort of control for human effort. And then what you're looking at here is the like time averaged area under the curve for that interaction. So basically, if you get the model, 10 minutes in, or I guess 1 minute in to be really accurate, then you'll do better than if you get the model 5 minutes in to be really accurate. And so that's what's being measured here. And so in terms of the like actual number of examples that get labeled, it varies from person to person. I don't actually know off the top of my head, but I want to say it's on the order of like 10 to 20.
Yeah, not bad. Yeah, that answers it. Thank you.
Cool. Yeah, any other questions about this first half before we move on? Okay. Cool. And I forgot to say, although we'll do more acknowledgments at the end, that this was led by Alex Tamkin and Belinda Li. Okay, excellent. Moving on. Oh, sorry, not moving on. Popping up. So the sort of first half of the talk was about efficient ways of getting natural language information about a task. And we saw that if you just take that information and you stick that information into a prompt, it makes us better at this task. And so a natural question to ask now is, are we done? And is there anything else that we can do? And so that's what the second half of the talk is going to be about. And this is work that was led by Feyza Akyürek, who was formerly at BU and is now at Scale. Good. So to start by kind of taking a recipe from the previous section, we gathered a bunch of information. We produced a new model that was updated to use that information, and we did this via prompting. And this is nice. If we abstract away this recipe a little bit further, it looks something like this, right? A way to update a model is to prompt it with some new piece of information, and then get the language model to perform a new task conditioned on this new information. This is the entire modern language modeling paradigm. Is incredibly effective, and it works across a wide range of tasks. However, it might not be enough. And a sort of classic example of one of the reasons that we might want to update a language model to, or the classic example that it might not be enough and that we might need to think about other ways of getting updates into language models is neologisms. So this is a paper from some folks at Georgia Tech, where they're observing, right, that many new words have entered the English lexicon since models that people are currently interacting with were trained. We have maskne, we have doom scrolling, we have barbiecore, and it would be sort of unfortunate if every time, a new word appeared in the English lexicon or in the lexicon of all of the languages that are spoken in the world, we had to update some system prompt somewhere with some definition of that word. And every new fact that appeared in the world also had to make its way into the system prompt. And so as a sort of extreme example of this, when I gave a first version of this talk that I'm giving now at Harvard last year, the Kempner Institute at Harvard is written by Sham Kakade, who, if you haven't interacted with him, has a very characteristic personal dress style. Suppose we wanted to introduce some new word into the lexicon, like right now in this talk, called Kakadikor, and saying that this is an aesthetic characterized by classic men's tailoring, ascots, and so on and so forth. Obviously, if you just take an off-the-shelf language model and you ask it to use this word, you get some nonsense out, right? This is a word that we just made up for this talk. How could it possibly know what this made-up Kakadikor word is? And here what you get from GPT-4 is that it's from Australia, it's named after the Kakadu National Park, blah, blah, blah. Now, calling back to the beginning of the talk, right, it is very interesting to note that the default behavior from this model is not to ask, what is this made-up word that you just presented to me, but instead to hallucinate a definition for this word. But, sort of similar to emphasize the effectiveness of prompting, right? If we simply insert this new piece of information into the context of our model, it's actually pretty good at using it and you get a sensible response out. And so the issue, as we said before, is just that you can't have all of your training data in the context all the time. And in particular, right, when these slides someday make their way into the training data for GPT-6, and if we're lucky, this new word that we just made up enters the vocabulary, we know, right, that at best, that language model is going to get one step of gradient descent on one sentence introducing the definition of this new word. And this is certainly not going to be enough to make it represent the sort of complex set, like it says here, of contextual relations that and conceptual relations that this word participates in. And again, I think these neologisms are especially nice examples to think about, because if you think about the sort of extreme version of this, where every word meaning in a language has to be provided in context, then every time your model does a forward pass, it's having to relearn the entire language from scratch in order to even begin to interpret what it is that the user is asking you to do. And this is clearly not going to work in the long term. All of this comes together to make a point that I think is actually kind of subtle, but which is as follows. The models that we have right now are pretty good at modifying their behavior in response to single new pieces of information when you put those pieces of information in context. And the issue is that you just can't put everything in context all the time. And so in particular, if we want to sort of, going back to the very high level motivation at the beginning of the talk, build systems that learn persistently from these kinds of interactions that we were talking about, we almost certainly need some way of getting whatever information we're learning from those interactions into the weights of these models and not just in the contexts. And you can see results of failures to learn from facts that are always expressed in a particular way, or only a small number of times in the training data. Here's the I think now it's somewhat famous reversal curse paper, right, that notes that you can ask a model who is Tom Cruise's mother, and it'll say Mary Lee Pfeiffer. You can ask the same model who is Mary Lee Pfeiffer's son, and it'll say, I have no idea who this person is, and they definitely don't have a famous son. Okay, so how do we get around this? How do we build models that don't just sort of learn to imitate the text in their training data, but that actually learn from the content of their training data in a really robust and persistent way? And the big idea that we're going to use here is actually a relatively simple one. We're just going to sort of take advantage of the fact that the prompting thing works and that the in-weights learning thing doesn't. And when we get a new piece of information, we're going to stick it in the context. We're going to prompt a language model to generate all of the documents that would exist counterfactually in a world where this new piece of information was true. And then we're just going to fine-tune our model on the data that falls out as a result. And maybe more surprisingly, we're going to see if we can do this even without starting with any new human-generated data, but just as a way of sort of picking up a model and shaking it and making it better on its own. And so in particular, if we think about the recipe on this slide that just says condition on some information, generate synthetic documents based on that information and fine tune, you can imagine doing this if your information comes from a trusted source, like an interaction with a human user. And this will then give you a sort of method of fine tuning models to be more factual. You can imagine conditioning a language model on some new information that's occurred since training, like our new word definitions. And this is now a mechanism for editing models. Or you could imagine doing this conditioned on information that was generated by the model itself, maybe as a result of some kind of reasoning process. And this, in principle, is going to give us a mechanism for training models in an unsupervised way to just be more internally consistent. And so we call this method overall deductive closure training. There's going to be one little extra thing that we do in this loop. So what this is actually going to look like is that we're going to prompt a language model to generate a bunch of related facts and annotate each of those facts with the probability sort of marginally that the language model thinks that fact is true or false, and to annotate all of these facts with the logical relationships that exist between them. And so if it thinks a pair of facts are contradictory, it'll label them as such. If it thinks they entail each other, it'll label them as such. And so once we've gotten all of these generated documents out of the language model, either unconditionally or prompted by some new piece of information that we really want the language model to learn, we're going to look at this complete set of facts, and we're going to identify, using something that looks like a SAT solver, the subset of these facts that are internally consistent according to the language model and marginally most likely to be true. And notice that this consistency check step, right, is a much, much easier task than knowing what is true out in the world, right? We've had models for a long time at this point that are good at natural language inference. Looking at a pair of sentences and judging whether they're sort of contradictory or non-contradictory is a super easy task. And that's all we need once we've had the model sort of vomit out everything that it knows about some particular domain or that it thinks is related to some new fact. And once we have this set of things that are internally consistent, we're just going to take them and we're going to fine-tune the model on them. Now, I want to note that there's been a bunch of work doing this kind of reasoning at inference time, including a long series of papers from AI2 that we were really inspired by here. And in some sense, the main observation that we're making is that you can just do this at training time before the user has actually asked your model any questions at all. Just fine-tuning the model to sort of upweight the probability of statements that were inferred to be true, downweight the probability of statements that were inferred to be false, where these statements were all generated either unconditionally or in response to some new piece of information you got from a user. And what this is, in theory, optimizing us towards is models that produce coherent outputs, not just the level of individual queries, but really in a kind of global sense. And so, like we said before, there's work on both sort of test time like inference for internal coherence and a bunch of other work on sort of continual learning, some of which came out after this paper in this same paradigm. And the cool thing, just to say this one more time, is that you can apply this recipe in a bunch of different ways. You can do it unsupervisedly by just sampling the text on some topic of interest directly from a language model, getting it to generate everything that it thinks is related to that topic, and then fine-tuning. Or you can do a supervised version of this for applications like model editing, where we take some new fact that the language model doesn't think are true. We ask the language model to generate all of the implications of that fact. And when we do this reasoning procedure, we peg the probability of that fact to be 1, such that the language model is now going to be forced to downweight anything that contradicts it. And this is then a way of sort of getting it to learn all of the logical implications of this new piece of information and not just to memorize the new string. Empirically, what's sort of exciting here is that this gives you both a good procedure for totally unsupervised improvement of a language model, and that's what we're looking at here, and state-of-the-art editing, which I'm not actually showing on this slide, but I don't know where that slide went, on sort of knowledge editing data set. And so this turns out to be better than standard retrieval-based editing methods and standard, sort of mechanistic in-weights things that try to localize the specific representation of an individual fact. Another cool thing that you can do, oh yeah, so sorry, this is looking at how well you can do at unsupervised fact verification. This is looking at how well you can do on both unsupervised and supervised editing, whether or not you know the target question at test time. Sorry, my slides are way out of order here. This is how well you do on on an unsupervised fact verification task. This is how well you do on a supervised model editing task that requires the model to make a bunch of sort of multi-hop deductions. A cool thing that you can look at in the unsupervised case is how often the model will give contradictory responses to two different questions, and this kind of training procedure dramatically reduces the rate at which models across prompts give answers that are inconsistent with each other, so it's becoming more internally coherent. And some other evidence of that is that if we go back and look at these reversal curse examples that we started with about Tom Cruise's mother, this substantially improves performance over baseline at models' ability to generate not the forward directions of their questions, but the reverse directions as well. And I think a thing that's important to point out here is that in these experiments, we're using the same prompt for the generation set as everything else. We're not explicitly telling the model, take the sentence and reverse the relation. We're just telling it generate everything that's logically implied, and it gets it a large fraction of the time. I'm sure you could get to 100% this way if you wanted to sort of specifically target the data set. Cool. So to, I guess, summarize this second half of the talk, if we want to learn efficiently from language, that's going to require us to be able to learn the implications of our training data and not just the surface facts. And what's nice is that even not very big models can do a pretty good job of inferring these implications once you put the new facts in context. And so even if sort of fine-tuning on a piece of text doesn't immediately give you for free all of the logical implications of that text, models can generate in context all of the stuff that is logically implied. And we can use this, again, both to do model editing and to do sort of unsupervised learning. Good. So to sort of put the two pieces of this talk together, and this is where things start to become more speculative, there's still a lot of problems that we have with the models that exist today, right? It is sometimes the case that models can describe procedures, give you an algorithm for solving some problem like arithmetic, but then fail to implement them when you actually try to get models to run those procedures by hand. Models are sometimes on the opposite direction, able to solve problems, but not to tell you either accurately or faithfully or reproducibly what algorithms or what heuristics they're using for solving those problems. It is a sort of persistent problem that models external expressions of uncertainty, the set of contexts in which they're willing to say, I don't know, is only very weakly coupled to their internal representations of confidence. If you look at things like probes, or even if you just look sort of behaviorally at other measures of model calibration. And finally, there's a bunch of, sort of cases where you get different answers out of a model when you ask them to think step by step or not to think step by step. And they're not always very good at figuring out sort of in what context it's appropriate to think or not think, and when that's going to change their answer. And maybe the sort of a high-level claim that I want to make here is that the two pieces that we saw in this talk are actually pretty good ways of addressing both of these problems, right? We saw, on one hand, a mechanism for generating informative pieces of natural language supervision that we can elicit from a human user, or in principle from a model itself. And on the other hand, a mechanism for turning small amounts of sort of rich natural language supervision into large amounts of synthetic training data that we can use to push this new information sort of really deeply into the model. And so if you imagine putting all of these things together, it might look something like the following. For whatever behavior we're trying to get into the model, right? Whether it's describe the algorithm that you yourself are running, or describe the conditions under which you are likely to answer a question wrong, or describe the logical implications of this new fact. Step one is, sort of coming up with a good question about this model behavior that we're trying to elicit. Step two is generating the synthetic data implied by the answer that you get from the user or the model or the data set. Step three is fine-tuning the model to sort of absorb this new piece of information and everything that implies. And step three is to rinse and repeat. And I think there are a lot of different problems that we could imagine tackling using some kind of recipe that looks basically like this. And with that, I will wrap up. As always, all credit goes to the people who led these projects, in particular, Belinda, Alex, Kunal, Feyza, Ekin, and Leshem, and all of our collaborators. And I will wrap up there. Thank you.
Awesome. Thank you. So we'll take some questions now. We have a good 10 minutes. We can have some discussion as well. So people online, please feel free to unmute yourself and ask questions directly. And if anybody in person wants to ask a question, you can just come to the screen and ask a question.
Okay, I'll just ask on the screen, using my laptop. So thank you for the talk. It's really interesting. I have a question about especially the last part of the talk about deductive closure training. When we synthesize pieces of information from the like the implications of the data, and then we try to fine-tune the model, does it increase hallucination? Because intuitively, the synthesized method, it looks like it will increase the risk of hallucination a lot. And I wonder whether the project evaluates this aspect.
Yeah, so this is a great question. And I guess there are a couple of ways you could answer that. One is just to look at accuracy, right? And to say that my proxy for whether the model is hallucinating or not is it generating more right answers or more wrong answers? And I think the surprising thing there is that the unsupervised version of this procedure actually, for that definition of hallucination, decreases the rate at which hallucination occurs, right? Makes the model more accurate without more training data. And I think the intuition there is that in some sense, like, the truth is internally coherent. And if I ask you to write down everything that you know about some problem domain and then reason about all of those facts collectively, probably your answers are going to get better rather than getting worse as a result of that reasoning procedure. And so when we're, generating stuff from the LM over here, in some sense, we kind of hope that it's going to hallucinate a little bit in writing these facts, that it's going to write down things that are factually incorrect. And that then when we look at all of the sort of entailment and contradiction relationships between these things, we'll recognize the hallucinations as hallucinations and we'll sort of squish them out of the model. Now, another way you could answer that question, or another sort of property you could want models to have, is that in those cases where you haven't, as a result of this reasoning procedure, figured out the truth or falsity of some particular statement, that models should say, I don't know, in those cases. Or that when you ask, is the statement true or false, that the model's confidence on, the weight that it puts on the words true and the words false is pretty close to 50%. That is not something that we evaluated in this paper. If I had to make a guess, that kind of hallucination probably gets worse. Models are probably more confident in their wrong answers than before this procedure, just because we're encouraging them to push mass onto either the yes or the no of a binary question answering task. We have a bunch of work going on in the lab right now on other kinds of objectives that you can use to improve models' calibrations and basically say, I don't know, when they're supposed to say, I don't know, but I don't think you get it for free. And yeah, it's a great question.
So, yeah, another question on, yeah.
Yeah, so when you ask the model to do the implication, do you start from a truth or a fact or a statement that is verified at the first place?
Yeah, so I know I went through these experiments really fast. We have a couple of different versions of this. So in the unsupervised version, which we're looking at on this slide, we basically say, here are some questions that you're going to be asked at test time. I'm not going to tell you the answers to those questions, but write down everything that you know about the domain in which these questions occur. And I think even for sort of purity's sake, we don't, it gets to see the questions when it's doing the generation, but we don't fine tune on the answers that it assigns to those questions. And we just sort of enforce internal consistency without using any external source of ground truth. But the other thing that you can do, and we do this both in the sort of knowledge editing case and in the supervised fine-tuning for factuality case, is that we start by saying, here's one fact that we know to be true. I don't care what probability the model assigns to it. When I do my fine-tuning procedure, I'm going to require that that fact is in the set that gets kept around, and I'm going to require that all the logical consequences of that fact are in the set that gets kept around. Yeah, and so in some sense, the difference is just like whether you tell the model the probability of the seed fact from which everything else is generated, or whether you let the model assign its own marginal probability to that.
I see. So, so my understanding is that for the unsupervised case, the model may actually result in a set of counterfactual statements, right? But in the supervised pattern, you are guaranteed to result in a set of factual statements.
Yeah, I mean, guaranteed as long as the implications are all assigned correctly. And I don't think we ever looked at a implication level, what fraction of those are right and wrong. But again, that's like NLI is an incredibly easy task, which is a weird thing to say, but is true in the year 2024. So
cool. Thank you. Yes.
Yeah.
I have a couple of follow-up questions on the questions asked right now. One, again, I wonder about the scale of at least the examples that you're showing me, the scale does not look huge. And I don't know if, you had big paragraphs and the graphs were huge as well. But I wonder that instead of directly just fine-tuning the LLM on these facts, what if I just provide all these different implications as part of my in-context examples and provide to the LLM, and does the performance improve similarly? So the point just being that fine-tuning is an expensive operation, and with a lot of closed models, you might not just be able to do that, but is this a good method to just improve the prompting itself, to reduce hallucination, to improve performance, etc.? Do you have, yeah.
Yeah, that's a great question. And one way of then thinking, so I don't think we have that baseline in here. One way of thinking about that is that it's just fancy, or a particular style of chain of thought that you might want to instruct the model to use. And again, I think there is so the closest thing to that, which is not exactly what you're describing, is where are these results? Oh yeah, these inference time baselines. So this graph inference thing in the last block here, where the model knows what the question is at test time. You have it generate all the related facts, and on the fly, you reason about the consequences of those. We're not doing the prompting thing that you just described. We're letting the sort of resolution of which of those facts are true and the influence of them on the final answer be resolved offline. I think so. There's both an AI2 paper that does this and a Stanford paper that does this. I can't remember the first author's names. I think they might have chain of thought baselines and find that this works better, but we didn't replicate that. But yeah, I mean, I think this whole thing is in some sense closely related to chain of thought distillation. And another thing that's in this general idea space is, you would like models to either produce the same answer immediately that they would produce after a lot of thinking, or if they know those things can't be made the same, to refuse to answer without being in chain of thought mode. And I think that's another place where you could sort of apply this this kind of self-consistency training.
Sounds good. Maybe another clarification and quick question here. I look at in the graphs, you had some of the ones which were marked as cross. Do you exclude them from training, or do you also train them saying that this is not true kind of thing?
Yeah, so we're explicitly training the model to the formatting is a little different depending on whether, a QA style thing or just a factual statement. But yeah, we're explicitly training the model for the things that get X'd out to say, is the following statement true or false? Statement, say false.
Okay, got it. Okay, that's good. Cool. Any other questions online?
Maybe another last question. I wonder whether you tried an alternative, sorry about the echoes. I wonder if you have tried another alternative baseline by retrieving like the implications about this statement from online and then SFT the model using the retrieved facts. So you can assume that the retrieved information are, so they are not synthesized, but you can assume that they are true. And they can also be perceived as like the implications.
Yeah, so we haven't done this with web search. We have done this with like RAG for these model editing tasks, and it doesn't always work super well. I think largely because when this is a data set with like multi-hop implications in it, and it can be hard to figure out which document you want to retrieve if that is like a hop away from where you started as a result of one of these edits. You know, I think for stuff that like is true out in the world and you know, is factual and is accessible via web search, certainly the best way to do all of these things. And right, the way like big LLM providers do this right now is literally just by going out and doing a web search. And I think, again, we're interested in the kinds of, like, it would be unfortunate if you had to Google the dictionary every time you wanted to read a new sentence. And I think those are the kinds of edits we're interested in making.
Okay, awesome. Yeah, we are about hitting the clock right now. So we'll end the talk right now. Let's thank our speaker once again. Thank you, Jacob, for this amazing talk and answering our beautiful questions. I think we can have a short break now for you as well. And I think Ashima will resume at 3:30, right?
Yeah.
Yeah, so we'll resume in roughly 20 minutes, I think. Okay. We'll use the same Zoom link. So the people who are gonna speak, you can just come back at the Zoom. I'll keep this open and we'll use the same Zoom for the individual one-on-one chats as well. Okay.
All right, perfect. See you soon.
Thank you. Thank you.